Hello, I'm Robin. Welcome to my shop. This video we're going to look at chuck stops and two different chuck stop systems that I've done for my chucks. And I've noticed Stefan Gottsvinter did a video based on stops he made that he was inspired by I guess one of my caliper videos where I showed my chuck stops just in passing. And Tom Lipton also did a Instagram post showing some stops, nice stops he made for his four-jaw chuck after visiting here and seeing the stops that I made. So glad I could be an inspiration to those guys. It's an honor, and it's good to be back. Thanks to all of the subscribers who asked where I've been, and hope I'm coming back. Yes, it's been 4 months. Been crazy busy. I'm not going to discuss it here, but that brings up a topic of please comment on your suggestions for a name for a catch-all show or video series. Similar to Tom's Monday Night Meatloaf or Adam's Saturday Night Special, a catch-all thing. I don't want it to have a day because I'm not guaranteeing I'm going to do one every week, but a catchy name that any suggestions would be appreciated on a catchy name for just a catch-all show or showing tips and various things and chit-chat about what's going on in the shop and things that some people might not be interested in that are more project oriented. So please send in your comments on that. Be glad to look at those, and hopefully you guys have some good ideas there. So let's get on with showing the different chuck stop systems and the design aspects of them. This video is not going to have any actual construction because I've made these before I was actively doing machining videos. And but the engineering thought processes and things may be of value, and just seeing the actual design aspects here may inspire how you approach making some chuck stops of your own. So let's get to it. I'm going to take off the 6-inch regular jawed chuck so we can put our internal stop in, and this is the small diameter chuck stop. If you have a lathe with a integral 5C collet or a 5C collet adapter that can reside in the spindle while you have a chuck on, this is a very handy technique. While I'm putting the collet in here, it's a good opportunity to show the 4-degree tapered nose Harding spindle style. Some people have asked, well, how does that thing work? And what it is, there's a slot here for there's a single pin in the chuck. There's a slot here that runs on a 4-degree downhill into the spindle because this is a 4-degree taper. It runs downhill 4 degrees, and then on either side this slot moves to the back as it moves either direction. So if you're going to do normal turning, normal direction, as you put the chuck on, you go on and then you go like this, and that pin just sucks the chuck back onto the taper. When I first saw this when I was a young machinist, I thought, man, that's flimsy. I just can't believe that little teeny 150 thousandths pin is going to do any good. Plus it's off center, it's going to push on one side and cock the chuck, but in reality it works extremely well. It just works. There's the matching pin in the chuck, and you can see that that's just in there. There's a screw hole in the back here to replace that. It's just a long 1/4 20 screw with that nose turned on it. It's not even hard. It's just the heat treat of a good grade 12 socket head cap screw, which is decent, maybe 150,000 tensile strength, and that's it. And it's just a very precisely matching taper, and it really does work well. Back to our chuck stops. We line up, put in a 1-inch collet, and here's our stop, and we put this in, set our collet closing pressure, so that when we put this in, this locks and we have our whatever position we want here. Okay, and we take this out now that that's adjusted, and we put our chuck on right over top of this. And that's all you do is just put that on by, as far as the system goes for the taper nose, just put it on. You never want to put the lock in and smack that chuck in place with the full inertia of that chuck. You just want to put it in and just give it a gentle like that. That's all it needs. You put it on much tighter than that and you're gonna have trouble. Or if you forget to lock it and you turn the spindle on and the spindle runs into the pin hard, you can get it on there really tight. Now I take my stop bar with the appropriately sized ring for whatever work I happen to be doing. I put it in, and now I can set it to whatever projection I want right here. Now these will run probably within 1,000th or two facial run out just from changing them and putting them in, because this is a hardening ground bar and the bores in these rings are pretty precise. But the bottom line is if you need it more accurate, you just take a skim cut on this while it's in and you've got it running dead true, and then you can put your parts in, and it doesn't matter how thin or deep, or if you need to change it a couple times for the part that you're working on, you can quickly just take this thing and push it in. You can get it out of the way if you need to drill through so you don't run into it. Then you can put this back in place to support the part so that the turning loads don't scoot the part back in the jaws if you're chucking something where you're gently chucking it so you don't distort the part. So here are the stop rings. I think I made these out of 416, just the material that I have on hand. They go from 2 3/4, 2 1/2. I think these are in 1/4 inch increments. Yeah, 2, 1.5 inches, and 1.5 inches, 1 3/4. Yeah, so 1/4 inch increments between them. A relatively precise bore to fit on this. This is what do you call it? Linear shafting, where it's case hardened. 60 case rod or linear shafting, whatever you want to call it. So this is a nice uniform, smooth, relatively non-deformable surface that allows these to go on nicely. Good collet grip, nice match on size. And the reason for them being relatively precise is that when you have a set screw situation like this, if these are a nice ring fit like this, okay, where they're smooth, the way that they seat on here as far as alignment will be better, which means that they are going to run truer. You don't want to have to skin these every single time you put it in if you're just doing work where 1,000th or two facial run out is okay. Not that that's the end of the world. I mean, it's a real quick operation, but this whistle notch here and a basically spherical end on the set screws allows these to go in and line up such that these don't skid from axial pressure from the parts. So, and it gives it a consistent end position. So when you put these on, you feel for the notch and tighten them up. So that's the system for work that is below 2 3/4. The reason you need this is because the way my other chuck stops are designed, they can only reach so far into the chuck. Two other little design notes. I made this relief enough such that these nested, so sitting on my shelf these all stack in each other without sliding off, just as a storage method for them to sit on the shelf. And on this end, the opposite end of the whistle notch, I have relieved this and just have this hardened edge so that if I have things smaller than the 1.5 inches here, I can actually put this in by itself and run right on this edge as far as a stop for things below the 1.5 inches, down to obviously 1 inch. One time saver has nothing to do with chuck stops, but has to do with just saving time, is having a chuck for external normal jaws and then reverse jaws, having two separate chucks so that there's no changeover time for those. Literally just spin the chuck on or off. And obviously it only takes a second to switch chucks on the hardening taper nose. Most chucks are relatively quick to change, much quicker than changing 3 or 4 or 6 jaws on the master jaws. So I have those two, and then I have a chuck in the back that's a dedicated chuck just for soft jaws. And I will cover design of a range of soft jaws in another video. Here are my stops, one for the reverse jaw chuck, one for the normal jaw chuck, and they are in the drawer with the corresponding wrenches, and then they're in there with all my other soft jaws and spiders for the soft jaws in my other chuck drawer. This is the chuck system for things that are past the range of the collet discs that I just showed you previously. So these need to be for both my regular jaw chuck shown here, and my reverse jaw chuck, which I'll also show. So design-wise, look at this and say, okay, what's typically going to go in here? It's not just external gripping that you'll use these stops for. Sometimes it's going to be internal gripping, how we have it shown here. So there'll be times when you want to just grab the ID of a part that you're going to face off thin, and you need these to be able to reach and get to where you want to grip, and also could be out of here on this lower level. So that's why I have the two steps here. You have to remember that you have a length of engagement of threads in these sections that limits how far you can adjust. So obviously you can get more adjust on this because you can have the full thread engagement with this all the way down. Gives you more travel available. Correspondingly on the shorter end you get less, so that's why there's two different levels here instead of having one that has to move further. The snug principle here, the split with the ability to actually pinch the threads, is very important because these need to stay put and be rigid once you put them in place, and preferably be able to lock them. So that's why we have these 2.5 millimeter pinch screws that actually pinch that like a clamp collar on those threads. So I look for a way to get the adjuster screw that I'm after, and here I say, okay, I use an M5 socket head cap screw, and that way I can get the threaded section versus the cylindrical section, whatever lengths I want out of this, just by whacking off the screw where I'm after. And the other design decision is, okay, what size hex can I put here that will get me out to the sharps? It turns out that 4 millimeters works out nicely. Now these screws are heat treatable material. I think there's something in the range of like a 4340. The screws, the grade 12 socket head cap screws. So what I did here is I did all this machining in its as-is state. Then I used a case hardening material. In this case, whatever it's called. Well, there's caseonite and then there's cherry red or whatever. I used the cherry red stuff. Basically a powder that infuses carbon into the surface of the steel, increases the carbon content, such that when you quench it, you get like a very mild case hardening. So that's what I did to these, and after I did that, I also tempered them again, because you don't want these to be brittle, even though they're just in compression. There's no actual loads on these other than, you know, resisting loading. You still want to temper them back to make sure that they don't crack. Another thing to keep in mind when you're using these materials, caseonite or the cherry red, it takes time for that stuff to infuse the carbon into the surface. So if you just dip this thing and hold it red for a few seconds and quench it, the depth of case that you get on there is going to be, you know, insignificant. So you actually need to hold these for a while and, you know, give them a good, you know, 5 minutes of dipping them in the material. It kind of gets into a thick, lazy stuff and it drips off and everything, drips new material, and hold it on there for a while such that you actually get a case that actually does something. Now this material also hardens reasonably hard anyhow. I just quenched them in water. That's probably a little extreme quench rate for this material, but I just wanted them to be hard so that they stood up nicely. So just some pointers about realizing that stuff doesn't just instantaneously put a deep case on. So those screws are made. Another note is that once these are done, keep in mind I only did the hardening on the ends here. Then the rest of it, once they're done, after these are slit, we actually take these and crunch these with the vise until they yield to where they're relatively draggy on the screw as is, that the screw's not rattling around. You don't want to use up all of the strength of this screw in just deforming this to get to the point where it touches, and have no no screw strength left to actually tighten on these. So by leaving the screw out, crunch these till it yields and get them crunched down, wrapped around until they are snug to begin with, then the screw only has to supply enough force to clamp. Then another thing is, since these threads are rolled, they're not always perfectly round, and you'll get some lumpiness in these as you turn them. So using a fine non-charging abrasive lapping material, either garnet or the QuickTime, I think it is, lap material. That's basically a non-charging lap material. Run these in with oil, run them back and forth with a drill, and lap those threads in, so you get nice smooth transitions. So when you're working with these, when you're using your nut driver or your wrench to move these in and out, you're not getting this lumpy tight loose, whatever. You get a nice smooth operating screw. So 2 notes there, pre-yielding this to get this down to a diameter where it's a snug fit on the threads, and lapping is a big deal in these working real nicely. Another feature is the 10 degrees I put in here just as a means for this to sit back tight against the clamp shoe that you'll see down here. Relatively simple way to have the part actually held. Yes, you can put these out and hold them and get it to clamp, and it could scoot in, but if you just gently hold these against the stop block, the clamp block, they clamp up nicely. This is the one for the this chuck, as we see here, and obviously we can get at these 2 screws no problem because of the way this is staggered. But this one is the one for the opposite chuck, and here I'm sorry, it's not. This one is. Yeah, sorry. This is the opposite. So this is the one that's in this chuck here. This is the opposite. It's got the tall leg on the outside, and that is for this chuck where the jaws are reversed. So you can see the difference there. But the thing to note here is, this design-wise, I had to make sure that I can still get in here to get to my screw. So in laying this out, making sure that I have access to get into the screw to tighten these. So exact same thing, except a sort of a thus and opposite hand version of here. And here is the clamp block that mounts on. And you can see the 10 degrees in there. And obviously we have a little heel on here. There's only about a 60 thousandths wide heel here on the tail end. And then this is all relieved here, and I don't take these on and off now. I just leave them on. I slide the block out, snug them on the chuck, and leave them there. Then we also have 3 holes so that this block can be moved to whichever position it's in. So if we're in further, we put the block in this way. If we're out here further, we just take the screws out, move the block over one, and that would be the position we see them in here, where it's out here on the outside. And then the screws that aren't used are masked with a little set screw so that they don't fill up with chips, and then when you go to put screws in, you're spending 10 minutes blowing chips out and trying to get so you can get a screw in there. So we just run a little set screw in to keep the hole masked while it's in there. So those are some of the design aspects. This is preheat treated 4142 material, still machinable, still easy to machine, but a little tougher than your average, low carbon rolled flat stock. These have been deburred, and then they've been tumbled. So you see that nice smooth, these nice, blended edges and no sharp corners. Just that's really what in my mind makes for a really quality looking product. It makes it look like it was a factory job instead of something just thrown together in the shop. So this is just a little Harbor Freight or hazard fraught tumbler with their small media in there, running there probably maybe 4 or 5 hours after they were deburred with a file, and just really gives a nice finish on all these edges. One design aspect that keep in mind that in the process of designing these, with a 6-jaw chuck, there's not a lot of space between the jaws. So that means that the actual how far these can move in before they hit the other jaw is limited. So therefore I designed the location of these clamping pads and how far these could reach in with that in mind, designing them to go in way further, even though you can back the jaws out far enough that they would be the stop would be able to get between the jaws. That's typically not going to happen. So the realm of where these are used is in this travel, which I will show on SolidWorks how I did the layout on these just as a double check. And obviously if I was going to use them out here, this is where I would unbolt this, move this over to this one and use these two bolt holes this way and put the set screw back in that inner hole so that the clamp is in a good bearing area. So you notice in both these cases, full in here I've got good full clamp bearing, and then full out when you move this out to the outer position here, it's got full bearing on there. And I'm not, the speeds that I would run these chucks, I'm not worried about centrifugal force being able to sling these out. When you tighten those two M4 screws, which have very, very long engagement in the chuck, probably like 3 diameters worth of length of threaded engagement, these aren't going to fall out. It's another note, whenever you have something tooling-wise, fixturing-wise, extra threaded engagement past the normal recommended amounts, like for example in cast iron, it's probably 1.5 times diameter is sufficient threads. But that doesn't take into account wear from grit and stuff on the threads and all those things. So anything that's going to have a lot of use all the time is going to get tightened fairly firmly multiple times. Extra thread engagement, if you have the ability to do it, is always a good idea.
Here I've laid out the chuck ID and OD. I've laid out a jaw at its correct width, and on the actual chuck face, I have in its sketch, I've put the line here showing where the other side of the jaw is, remember this is a 6-jaw chuck. So this is where, these dimensions are where the other chuck jaw lies, such that I know where the maximum distance in that the actual stop can go. And that's for planning purposes of where I put the clamp block. So going back to the actual view here and a component, you can see here's our travel distance that I've got set on in SolidWorks for the mates, such that it can go the full distance. And then here we can look at the end, we can see how I've designed the few degrees of tilt in the keyway, which holds this tight against the block, and of course the relief with a small heel in the back, such that we get good clamp action directly on the center line of this clamp block.
So one little trick here in using these is to set your calipers at the actual jaw height of the jaw that you're going to be using, and then zero it out in incremental mode, and then you can take this and set these heights to the amount of grip that you want. So in this case, the 158 thousandths, I could preset all these in the ballpark before I put them on the chuck to get the height I'm after, and then just use an indicator to tweak them into whatever level of match you're after. So with chuck stops, a lot of times you're using these because you're going to be doing something thin. Not always, but a lot of the time, it's the whole purpose of this is to get these things supported so that you can do something that's reasonably skinny. So I have this disc, aluminum disc, that's turned, it's maybe 190 thousandths thick. And I have these stops set such that we're gripping just by 1 tooth's worth, where these things have the grooves in here. Basically we're grabbing with 1 tooth here. So we're grabbing on basically about a third, the bottom third of these. And what I'm trying to point out here is that when you grab anything, whether it's in a regular machine vise or in a chuck like this, when you grab and compress with chucking force, the part is going to deform. And in this example here, I'm going to get a mag base, stick it on the side here, and obviously right here at the stop it's not going to move. But in here I'm going to show you what happens as I tighten this, that this is going to dish and rise up because we're compressing this lower section. The upper 2/3 is not being compressed, and this is going to start to dish and form a dome shape. Well, the problem is that if you're not aware of that, you machine this off. Let's say your lathe faces off perfectly flat. You take it out, and when you relax it, this now goes back to its at-rest condition, and this thing is concave. and you're thinking you've got a part that's nice and parallel, but you can't figure out why, when I face this thing, is it 15 thousandths thinner in the center here than it is out here. Well, it's because this grip is causing that condition. That would be cured by lowering these after you've machined this off till there's only a few thousandths sticking out here, and you're gripping completely where you're uniformly compressing the entire disc. Then you would not be dishing it as much. Or if you have a situation like on a machine vise, on a vise in a mill, you can actually put a wire or a piece of flat stock, small flat stock, at the center of the thickness on each jaw, such that you're pressing on the neutral axis. Then as you press, you're not causing it to go up or down. You're pressing right at the neutral axis, which would be the midpoint of its thickness, assuming it's uniform cross section, and the part would stay flat. So I'm going to grab an indicator on this, and we'll show you that phenomenon. Okay, I've got a 1/2 thousandth indicator in here. My stop is right here. I've got the indicator tip right over the stop, and I'm just tightening the vise fairly firm, and you can see I'm not getting any significant, carrying on here. Now I'm going to move over to the center and do the same thing. So the chuck's just touching now, not tight yet. I'm going to have to take my chuck wrench out and reposition here once as I go tighten this, because I'm running into the clamp that I had this clamp to the table with. So here we are. There's a little bit. Now I got to move to the next position to be able to get some more. And now that's good and firm. That's real tight. So there's like 4 3/4 thousandths of rise in this part, which means if you did both sides of this part clamped like that, you'd be like 9-10 thousandths skinnier in the center than you were on the outside, and you might even attribute it to your lathe not facing off perpendicular, when it has nothing to do with the squareness of your cross slide to your spindle. It has all to do with the deformation of the disc because of where you're clamping and your where the neutral axis of the part is relative to where your clamp pressure is. So just a little gotcha there for maybe less experienced machinists. This is a good example of thinking like a mechanical engineer. The more you think like a mechanical engineer in your machining, the better off you are. Analyzing everything as stresses, pressures, bending forces, yields. Thinking about doing a video on that of basically mechanical engineering for machinists. I'm not an official mechanical engineer, but I've done a lot of it, so I think I could give a good layman's term rundown of mechanical engineering as it applies to machining. That's really the key. I think a lot of your more experienced machinists, when you see them doing things, it's because they're thinking like a mechanical engineer. They're seeing the mechanics involved in their setup in their mind as they're doing it, avoiding a lot of the pitfalls that could happen.
Here I have the indicator in place. I'm zeroing it on the first post, which I have adjusted to the correct height and locked. Moving to the second one, coming up, seeing where I am, using the 4mm wrench to adjust the position. Obviously it's a little bit too snug with the clamp screw, backing that off a little bit so I can rotate the adjuster, cranking the adjuster down to 0. Actually we'll go past and back up in the direction that we're loading, and we're also increasing the drag on the clamp screw, so we just about almost can't turn it at the end there, so it's good and snug, so when we lock it up it stays put. That's a 5/10, 1/2 thousandths per division indicator there. And so we're good on that one. Go to this one. Whoops, that was pegged. That was all the way around to 0. I'm not sure if I bumped the indicator or not. So I'm going to jack that down so that we can go past. Now I'll come up on, yep, not past. Now I'm going to recheck my 0, reset my 0 on my first reference post that I used, and come back and hit this one. And there we're within the range of the indicator. It turns out I actually didn't bump the indicator, but it was close enough that it was a good thing to check. And go past again just like the second one, snugging up on the locking screw as we approach the 0, get good and firm so that we don't get any creep when we lock it. And we're good to go. Here we're putting a thin disc in, showing how it would work as an example.
Here's an example of using the chuck stops to be able to tweak a part in that's hanging out a long way. You can see my 1, 2, 3. It's the inner stop down here, not this outer one that is actually bearing on the chuck. I've used this to rough this very last section. I roughed this other section with it, grabbed more in the chuck, but now this final section I'm down to here. But I need to get the tail end to run true. So as you can see here, that's running very true out in the actual center drill hole. We accomplish that by being able to come in here and get on these little wrench flats on these risers and actually jack this, skid it in the jaws, and get that tail end to run true just by using those 3 points. Just like you'd use a buck chuck, you use these 3 jack screws to bump this around, and of course obviously then it firmly supports this against the end thrust of the roughing cuts. So you can see these stops are fairly versatile and quick. It can be argued that there's a place for soft jaws, and that is true. They take a lot longer in a lot of instances, so we'll cover that in another video. You can see there's an essence on efficiency in a lot of things I do and doing things quickly. Obviously I'm making a living doing this, so it matters. But just pick an arbitrary hourly rate, $60 an hour. That's $1 a minute, just to make the mental math easy. $1 a minute, it takes you 4 or 5 minutes longer to do something, or 4 or 5 minutes several times in a job to do something. That's $4 or $5, $20 that it just flew out the window because you were fumbling around instead of having a system that works perfectly and everything's tuned to just do the job properly. I realize a lot of you guys are hobbyists and say, it doesn't matter to me. Well, think about if you were just 25% more efficient in what you do as a hobbyist. That's 25% more projects done in your lifetime. In 10 years of your lifetime, that's 2.5 years worth of projects that you get done that you wouldn't have otherwise. So maybe just a little incentive to think more like a job shop machinist and think about time does matter. And if I really want to get a lot of projects done, I'm sure all of you have immensely long lists of projects that aren't done, just like everybody else. It could help you. So I hope you appreciated this video. I hope there was some content that was useful. If you like this content, please subscribe if you haven't already. Give it a thumbs up. Tell your friends. And thanks for watching, and I'll be back with some more.